In example number 4, work needed to empty a tank. A tank has the shape of an inverted circle cone with height 10 meters and base radius 4 meters. It is filled with water to a height of 8 meters. We want to find the work required to empty the tank by pumping all of the water to the top of the tank. The density of the water is 1,000 kilograms per meters cubed, or cubic meters. Now, let's measure depths from the top of the tank by introducing a vertical coordinate line, as you can see here in figure 3. The water extends from the depth of 2 meters to a depth of 10 meters. And so we divide the interval from 2 to 10 into n subintervals with endpoints x subscript 0 all the way to x subscript n. And then we're going to choose this x subscript I in the ith subinterval. This divides the water into n layers. The ith layer is approximated by a circular cylinder with a radius r subscript I, and it has a height of delta x. And so we can compute r subscript I from similar triangles using this figure number 4. So therefore, we're going to create this similar triangle. We know that this distance is 10. We know that this distance represents 10 minus x subscript I. We know that this is the radius of r subscript I. And at the top, we have a radius of 4. So we're going to use the idea of similar triangles to then solve. So we can say that r subscript I to 10 minus x subscript I is equal to 4 to 10. And now we can then cross multiply and then solve for I subscript I. By solving for that, we would end up with 2/5 times 10 minus x subscript I, which gives us the radius. Thus, an approximation to the volume of the ith layer of water is the following. So the volume of that ith layer is approximately pi r squared, or ith squared, times delta x. So the area then becomes 4 pi over 25 times 10 minus x subscript I squared delta x. And so its mass is the following. The mass with subscript I is equal to density times the volume. So we're taking the density, which is 1,000, times the volume, which is 4 pi over 25, times 10 minus x subscript I squared delta x. And if we multiply that out, we get 160 pi times 10 minus x subscript I squared delta x. The force that's required to raise this layer must overcome the force of gravity. And so F subscript I, which is equal to the mass times gravity, which is going to equal 9.8 times the mass, which we got up here, 160 pi times 10 minus x subscript I squared delta x. So if we multiply these numbers out, then we get approximately 1,568 pi times 10 minus x subscript I squared times delta x. Now each particle in the layer must travel a distance of approximately x subscript I. So the work done to raise this layer to the top is approximately the product of the force and the distance. So we're going to take the force and then multiply by its distance, which gives us the following result. 1,568 pi x subscript I times 10 minus x subscript I squared delta x. And so to find the total work done in emptying the entire tank, we add the contributions of each of the n layers and then take the limit as n approaches infinity. So the work, which is equal to the limit as n approaches infinity from I is equal to 1 to n of that function, going now from 2 to 10, of the function 1568 pi x times 10 minus x squared dx, then we can go ahead and then solve that integral. So we're going to go ahead and then expand 10 minus x squared and then factor out the constant, which is 1568 pi. So now we have the integral 1568 pi that goes from a lower limit of 2 to 10. And we've distributed the x and multiplied that out to get 100x minus 20x squared plus x cubed dx. And now we just need to take the antiderivative of all three terms. Taking the antiderivative of all three terms, we get 1568 pi times 50x squared minus 20x cubed over 3 plus x to the fourth over 4, going from a lower limit of 2 to an upper limit of 10, which then gives us 1568 pi times 2048 over 3, which approximately gives you in scientific notation 3.4 times 10 to the 6 joules.